Alright guys, in this video we're going to focus on one component of the fertilizer, and that's the most important component of the Kjeldahl method. Woohoo! Can you still spell it? I bet you can't. And trust me, I've been doing this for years, and it seems like I always get those letters backward in the word Kjeldahl. No matter what I do, it just doesn't seem natural to me. All right, so in the world of nitrogen, most of the time, there are two very common cheap sources of nitrogen that we can give consumers, so that way they can sprinkle it on their little flowers and make them grow even taller and bigger, and you'll be the talk of the neighborhood or the roundabout that you live on. Maybe not the roundabout. What do they call the ends of the street that just make circles? All right, so here is nitrogen, and nitrogen, of course, is the element from the periodic table, but nitrogen is a diatomic, and dia is 2, so therefore if it's not in a relationship, it can be in a relationship with its twin, and it is perfectly okay with that. Oh, go figure. So diatomic is one of the magic 7s that start at 7, and they make a 7 on the periodic table, except for that weird little bitty hydrogen in the top left hand corner. But NOFClBrIN hydrogen, there's your 7 that make a 7 that start at 7. So nitrogen is one of those, but that is not the nitrogen that we're talking about. No, it's not. So I'm going to cross out because we're not talking about diatomic hydrogen here. We are talking about nitrogen either in an inorganic source or an organic source. All right, so inorganic or organic versions of nitrogen. Inorganic versions are often what we refer to as salts. So many times they have a cation and they have an anion that they bring to the table. So for instance, a salt that you know is sodium and chloride. And sodium is a metal on the periodic table, a cation that creates a positive charge, and a chlorine is a anion because it carries a negative charge. And that cation and anion, or metal and non-metal, can come together and fall in love and make a little happy marriage. And that is sodium chloride, and that is table salt. And that table salt dissolves extremely well in water, as do a lot of the salts that we refer to in the group 1 and group 2 families. All right, so with that said, we have a inorganic version of nitrogen. And that inorganic version of nitrogen is ammonium for the positive piece and nitrate for the negative piece. So NH4 NO3. Now, I drew it here with the charges, and I did that just so that you know one NH4 group sticks together and one NO3 group sticks together. So these two groups see each other, they madly fall in love, and they all go into a relationship, and they're perfectly happy with all of that. So NH4NO3 come together as one, and I just need one ammonium and I need one of the nitrate. So this is ammonium nitrate. That is our inorganic version of nitrogen that can be used in fertilizers. And again, it's very cheap, it's easy to obtain, it's not going to cost an arm and a leg to buy the fertilizer as a consumer in the store, and it's readily accessible, of course, right? The other version of organic is maybe something that you're not as familiar with, and that's something called urea. U-R-E-A, urea. Urea has a funny little history. So this is organic. So what this means is that it is not necessarily going off of the cation and anion play. This works a little different. It's not really deemed a salt. It's not really involving a cation and a anion that comes together. It is more of a organic type of compound that is very carbon heavy sometimes, not all the times, but carbon based at least. And that carbon can bring with it friends to the party. And that's what's going on with urea. It's a carbon, and that carbon is bringing some buddies to the party that it's going to show up at. And because of that group that's showing up, depending on how it's made, that is what's called get an organic compound. So urea has the following structure. What we'll see with urea is that it is a carbon, and that carbon has a double bond to an oxygen. And then off of one side, so that's one buddy that carbon's bringing to the party. And off of one side, we have an NH2 group, and there is our nitrogen containing group, because that nitrogen is going to provide us some nitrogen content in the fertilizer. And then on the other side, the other buddy that it's bringing to the party is another NH2 group. So this carbon holds hands with three different groups. One is an oxygen, and the other two are the same, and those are NH2s in total. So a couple of pieces of terminology here that I would like for you to know. So if I go back and I take a look at this C double bond O group, this C double bond O group is referred to as the carbonyl. That carbonyl is very commonly found in many organic compounds. Carbon double bonded to an oxygen, for the most part, it's like, okay, just the general variety of a compound. I mean, that's just what goes on. There's so many versions of a carbonyl group that can show up in organic structures. And this is just one of them. But if I only focus on the C double bond O group, we have a term for that, and that term is carbonyl. Out of the carbonyl, there's many different umbrellas of compounds that can fall out. So out of this family of carbonyl is going to come something called an amide, and that is AMIDE, amide, little O amide, and little amide is carbon double bond O with a nitrogen off of at least one side. And this does meet that definition. It is a nitrogen containing compound on one side of the carbon. I know it's on both sides, but that doesn't matter. We still have an amide group. So the C double bond O is called a carbonyl. But if I wanted to expand by definition and be like, hey, what type of carbonyl do we have? And I look at what is connected to that C double bond O, we have another term for that, and it is a carbonyl containing compound. And that carbonyl functional group, in this particular case, is called an amide, A-M-I-D-E. Now, notice the way that this is made. It's not a full-blown positive. It's not a full-blown negative. It's not a cation and an anion that's hanging out together based on charges. This is an entire grouping of atoms that are sharing electrons. And these are representation of the bond. So there's 2 electrons in each line. So the electrons are making them hang out, and they get along, and they get along quite well. And all of those elements come together to make a molecule. And that molecule in this case is 1 carbon, 1 oxygen, 2 nitrogens, and 4 hydrogens in total. And that combination grouped together in that particular way is called urea, U-R-E-A. Now, urea is an organic compound. And I told you there's kind of a funny story here, because when organic chemistry first took off, organic chemistry basically meant that it was a molecule that was essential to life. And it had to be made by a living organism. That is kind of the old school version of what organic chemistry was all about. So your body had to use it, your body had to make it. And if it wasn't for your body, then this was not deemed an organic molecule back in the day. So for instance, there are things that make you work. There's things that make you tick versus some old rock that you find out in your yard. Now, maybe there's not drastically difference. I mean, you know those people, and I know those people too. There's not major differences between a rock and somebody or your best friend, maybe. Okay, so either which way, there are molecules inside of us that we need, that our body does make, and that is a little different than a rock that does not talk and does not think and does not breathe. At least I don't think they do. But either way, there's differences here, and there's drastic differences. So in the heyday of organic, when it was first kind of getting talked about, first getting defined, what we used is this word called vitalism. And vitalism was this idea that there were vital things that your body needed or life needed in order to exist. And those vital things were called organic compounds. That was the old school definition of organic versus non-organic. So organic, we thought, was essential to life, and life had to make it. We could not do that in a lab. The funny thing, though, is that very early on, after, well, not early on, but after that definition was defined, we had a scientist with the last name of Wohler, Wohler, Wohler. And Wohler comes into the lab and he's like, I just don't get this, because this doesn't quite make sense to me. These are compounds, these are structures, these are elements from the periodic table that our body's using, that our body's making. And I know good and well that we do not need human life or a life form in order to make these for us. And Wohler was the first to disprove what we call vitalism. And what he did is that he made urea. He made urea from scratch. And here's the thing. Urea is found in your urine. So if you go and you listen to these stories of these farmers and you're like, I'm going to spread pig manure all over my fields of corn, and I'm going to let the corn grow in pig poop, and then I'm going to gather it up and sell it to you, and you're going to eat it, and you're going to say, this is the best corn ever. What'd you do to it? Well, I put pig poop on it. There is kind of something to that. So part of urine that you make, that I make, that most things make, part of urine is a compound called urea that is found in our urine samples when we go and when we test them. So in other words, your body kind of makes urea. And by the old school definition, this was called an organic compound. It's still an organic compound today, though, but it's just an organic compound in a different way. So urea was deemed organic. Urea came from a human living, breathing thing. And because of that, Wohler went in and Wohler made urea from scratch without a person needed, without a life form needed. So he synthesized a molecule, and that molecule was deemed organic because it came from a living, breathing person, but now Wohler did it without that need. So our definition of organic changed at that moment. He disproved vitalism, and he said vitalism's not a thing anymore, and the reason that it's not a thing is because I can make it. I don't need someone to make it for me. So we can synthesize it in a lab. But because it's carbon-based, that's its structure, that's its building bones, because it's carbon-based, we are going to deem molecules now as organic for that reason. Not because they come from living, breathing things, but because they are carbon-based compounds. And that is how we still define organic today. All right, so now I'm going to go back to the structure of urea. We said it was a carbonyl, and there was an NH2 on this side, and there was an NH2 on this side. I want to talk a little bit about urea as a whole. So we already said one of the first organics to disprove what we called vitalism back in the day. So that's kind of the first big major player that did that for us. And it just so happens it's a common ingredient in urine, very easily accessible. Next up, it is very highly water soluble. Okay. Of course, that makes sense. It's in your urine, okay? And then next, it is nitrogen containing. Now, there are many compounds that contain nitrogen. This is just one of them in the world of organic, but it's one. And not only that, but urea is often very cheap, and it's very easy. Perfect dates, right? Cheap and easy. No, I'm just kidding. Or am I? This would be falling under the category of organic chemistry, but also organic fertilizer. So this can be used in a fertilizer that is deemed organic, because by definition it is organic. We do not violate that definition at all. But it's not our only choice, and it's actually not even the best choice, but it is a compound that is approved for use in organic, but it's also approved for use in inorganic versions as well. All right. One of the bad things here is that urea, just due to the way that it's made, it's an organic compound, not a salt, not an ionic compound, but that urea can actually lose ammonia, or in other words, nitrogen. So it can lose nitrogen over time. And this is going to happen just if it's been opened, if it's been sitting around for quite some time, if heat has gotten to it, direct sunlight has gotten to it. There's a number of different things that can go on in these fertilizers, especially in urea-based fertilizers, where nitrogen is getting lost, and nitrogen's getting lost through the production of ammonia gas, and ammonia gas is NH3. So I want you to keep in mind of a cha-cha like that, right? So that carbon is holding on to two NH2 groups, and at a certain moment in time, under the right circumstances, then maybe, just so maybe, that bond can be disturbed, or that bond is not as strong, and that bond can lose or break or cleave, and then we can get some NH3 that can get released from this molecule, not NH2 but NH3, and then that can just literally evaporate off, and we start losing our nitrogen content over time. So fertilizers are not label approved, I guess, after a certain expiration date, and this is one of the guidelines that they will use in order to determine what the expiration date might be. Now, of course, if you're keeping it outside in a very hot, humid shed, it's going to change versus keeping it inside of your house or inside of something that's a little bit covered. This is what urea looks like. Nothing special, nothing fancy. We're seeing a little bit of white crystal, spherical types of particles that come from urea. It just naturally is forming that way due to its crystal structure, but very easily soluble in water. That's great news, because we want that urea to dissolve in water when we put it into a watering pitcher, or when we put it out into our lawn and we take the sprinklers to it, or whatever the case is. This is not, though, the only option for urea or for nitrogen. And we already mentioned ammonium nitrate, so I'm going to give you a little bit of comparison here. The ammonia or ammonium is NH4. So this is a nitrogen, and it is surrounded by 4 bonds, so it completes the octet with hydrogens. And I'm just going to draw them this way, and that group carries with it a positive charge. So there is the ammonium piece that comes along with ammonium nitrate. And then nitrate is NO3. So there's an oxygen, and there's an oxygen, and there's an oxygen. There's 3 bonds that are there. We get a little bit of what we call hybridization, and that hybridization means electrons can move throughout the molecule. Not drastically important for this particular lecture or for this lab, but we do get some movement of electrons that stabilize that NO3 group a little bit more, actually, and then that carries a negative charge. So we have a 1/2 that's fully positive, 1/2 that's fully negative, and these two, like magnets, are attracted, opposites attract, and they kind of stick together. So the ammonium and the nitrate are not actually locked in key together, but they hang out, and you see one, you see the other one, and they're everywhere. When they go out together, you're going to see both of them at the same time. You will never see them really alone too much, just because they have those charges that are keeping them together and allowing their relationship to kind of work out for the best way possible. So this is another very cheap source of nitrogen. It's actually cheaper in many ways than urea is. And not only that, but it's actually widely available, more so than urea is. So you talk about easy, then this thing is like super easy to get a hold of. Soda or ammonium nitrate was used very heavily in fertilizers for many, many years. The problem is that someone wised up one day and someone said, hey, Well, if I want to make explosives, then I need some nitrogen containing pieces. And what better easy way to get nitrogen at my disposal than to go to any Home Depot, Lowe's, Walmart, big box retailer and go in and purchase bags of fertilizer. I'm just going to say I'm fertilizing my roses at the house, when actually really what I'm doing is probably making an explosive bomb in my garage that I can then go out and throw into a crowd or throw into a building or do whatever, crazy people do with it. So for that reason, they realized that the problem here was the fertilizer. So they wanted to restrict what the fertilizers could be used for, and there's a couple of ways to do that. And then one day, someone wised up and said, listen, let's just substitute this ammonium nitrate out of the fertilizer, and let's substitute it instead with urea. Urea cannot be used to make explosives very easily. Urea has a different type of chemistry. Urea is organic. It's not necessarily ionic. Urea still carries the nitrogen. Urea is still pretty cheap. Urea is still pretty available. So this would make a great substitution. And not only that, but urea is also found in organic fertilizers too. So it's appropriate to be used in either version that we want to market out to a consumer. So here is the deletion of ammonium nitrate, because we've got crazy people that want to do stuff in garages and secrets and blow themselves up. And we get a substitution of an organic compound instead. So it has been phased out. I'm not saying that it's totally out of fertilizers, but less and less sodium, or I keep saying sodium, less and less ammonium nitrate is getting used in modern fertilizers today out into the stores. And it really is for that particular reason. It's just the alternate uses of a fertilizer and what people can do with it. What's sad is that ammonium nitrate is actually more stable. So we talked about urea losing nitrogen over time. Ammonium nitrate doesn't really do that as easily. So it normally stays around a little bit longer. It's more shelf stable. My concentration of nitrogen is not going to change over a course of time. It doesn't lose that nitrogen rapidly at all. So that was the good thing about ammonium nitrate, and that's just because it is an inorganic compound and not an organic compound. Those salts, when they were formed, they are very strongly connected, and they don't really want to let go, Jack. Let go. No, Titanic. Ah! All right, so in the next video, we'll talk finally about our TKN method, because we've worked ourselves up to nitrogen and understanding the background and fertilizer and why nitrogen is in there. By the way, ammonium nitrate looks exactly like urea in a way. They're white little round spherical particles. I almost guarantee you if I put one in one plate and another in another plate, you couldn't tell them apart. So that picture with urea, just erase urea at the top and think ammonium nitrate. You'll find it just looking almost the exact same way there. So in the next video, we'll talk about TKN. We're going to talk a little bit about the history. How did this get started? What are some of the common uses, and what are we going to do with it with our fertilizer sample in order to make this lab method work? So stay tuned. We might have one video under our belt, maybe two, depending on how much I babble, and who knows, maybe it will be 15 by the time this is over.